Today we are covering section 11.1, chi-square test for goodness of fit. When do we use this? When we have one sample from one population with one categorical variable. Up to this point, we've been dealing with quantitative variables. Now we're talking about categorical variables. The test statistic is chi squared. Looks like a fancy X. That's the Greek letter chi. Chi squared equals sigma, which means the sum of the observed counts minus expected counts squared divided by expected counts. To find expected counts, we do n times p. To find the p-value, if you know the chi-squared test statistic, to find the p-value, you use the chart in the formula packet, which I'll show to you in just a second, or my preferred way is to go to your calculator, do menu, statistics, distributions, chi-squared CDF. Remember CDF because it's not equal to. Your chi-squared test statistic will always be your lower bound. Your upper bound will always be some really large number. Here's what the formula, or the sheet in your formula chart looks like. Notice the shape of the distribution. Notice it's no longer normal. It has it's right skew. It has a tail to the right. And notice everything is above. That's why your chi-squared statistic will be your lower bound, and a really big number will be your upper bound. Some characteristics of the chi-squared distribution. It's skewed right with only positive numbers. There's no negative chi-squared values. Your degrees of freedom are the number of categories minus 1. All your expected counts must be greater than or equal to 5. The mean of a chi-square distribution is equal to the degrees of freedom. For all chi-square distributions where your degrees of freedom are greater than 2, the mode or the peak of the distribution is at df minus 2, degrees of freedom minus 2. All right. How do we write hypotheses for this test? The null hypothesis. The stated distribution of the categorical variable in the population of interest is correct. The alternative. The stated distribution of the categorical variable in the population of interest is not correct. The conditions. Random. 10%. Those are the same as they have been. What changes is a normal condition. We no longer have a normal condition. We just have all expected counts are greater than or equal to 5. It's not 10 or 30, it's 5. All right, the calculator steps. Calculator steps, it's a little involved. All right? First thing you're going to do is open a list and spreadsheets page. Title column A, observed. Title column B, expected. Input your data in the appropriate column. Then open a calculator page. Then go menu, statistics, stat test, chi-squared GOF. You notice when you go menu, statistics, stat test, there's 2 chi-squared. For this particular test, you want chi-squared GOF. All right, let's look at an example. It says example, Mars Inc., makers of M&M candies, claims that they produce plain M&Ms with the following distribution. Brown 13%, red 13%, yellow 14%, orange 20%, green 16%, and blue 24%. In the table below are the observed counts from Jerome's class when they did the Candyman can activity. So what they did was they took a random sample of M&Ms. In this case, it was 60 M&Ms, and they wrote down how many they observed in their random sample of 60 were brown, red, yellow, orange, green, and blue. Okay? Assuming the company's claim is true, how many of each color would you expect in your sample? Calculate how many of each color you should have found in your sample to 2 decimal places. Write these expected counts in the table. All right, so to find the expected count here for brown, it's n times p. So my n is 60, and my p is 0.13, because for brown it was 13%. And that gives me 7.80. For red, it was the same thing, so 7.80. For yellow, it's 0.14 times 60, which gave me 8.40. For orange, I got 12. For green, I got 9.60 and 14.40 for blue. If you add them all up, they should total to 60. Okay? All right. So the next part. Is there any doubt of Mars' claimed color distribution? How closely do the observed counts fit the expected counts? They're asking us to do a chi-square goodness of fit test. Okay? So here we go. We will test the following hypotheses at the alpha equals 0.05 significance level. So the null hypothesis is the distribution of colors for all plain M&Ms, as stated by Mars Inc., is correct. The alternative hypothesis, the distribution of colors for all plain M&Ms, as stated by Mars Inc., is not correct. We will perform a chi-square test for goodness of fit if conditions are met. A random sample was taken. 10%. We assume 10 times 60 is less than or equal to the total number of plain M&Ms. Same 10% that we're used to taking. And then all expected counts are greater than or equal to 5. See table above. Please make sure when you're doing this condition, the expected counts condition, you either put all expected counts here where you're checking the condition, or you tell the person reading your answer where they can find the expected counts. You can't just say all expected counts greater than or equal to 5 and not show the expected counts somewhere. All right? So we're going to put all this information in our calculator, follow the calculator steps. You should get degrees of freedom as 5 because there's 6 categories. 1, 2, 3, 4, 5, 6. 6 minus 1 is 5. From the calculator, chi-squared is 10.18, and the p-value is 0.0703. Since the p-value is greater than alpha, we fail to reject H sub O. There is not convincing evidence that the distribution of colors for all plain M&Ms, as stated by Mars Inc., is not correct. Okay? One more example. In his book Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. Specifically, since January 1st is the cutoff date for youth leagues in Canada, where many National Hockey League players come from, players born in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time and more coaching and have a better chance of being successful. To see if birth date is related to success, judged by whether a player makes it into the NHL, a random sample of 80 NHL players from the 2009-2010 season was selected and their birthdays were recorded. Overall, 32 were born in the first quarter of the year, 20 in the second quarter, 16 in the third quarter, and 12 in the fourth quarter. Do these data provide convincing evidence that the birthdays of NHL players are not uniformly distributed throughout the year? Okay? So the first thing I'm going to do is make a table of observed and expected. I took the numbers from the problem, 32 in the first quarter, 20 in the second, 16 in the third, and 12 in the fourth, put them in my observed. To get my expected, if they are evenly distributed throughout the year, then I would expect a fourth to be born in the first quarter, a fourth to be born in the second quarter, a fourth in the third, and a fourth in the fourth quarter. That would be 20 in each quarter. All right? Now it's time to do our test. We will test the following hypotheses at the alpha equals 0.05 significance level. H sub O. The birthdays of all NHL players are evenly distributed across the 4 quarters of the year. You could have said evenly, the problem said uniformly, either one would work. H sub A. The birthdays of all NHL players are not evenly distributed across the 4 quarters of the year. We will perform a chi-squared test for goodness of fit if conditions are met. Random, it stated it was a random sample. 10%, we assume 10 times 80 is less than or equal to the total number of NHL players. And I believe I read somewhere that there were 870 something players during that time. So less than 900, but more than 800. And then all expected counts are greater than or equal to 5. See the table above. All right? So degrees of freedom is number of categories minus 1. There's 4 categories because there's 4 quarters. So 4 minus 1 is 3. After you put everything in the calculator and run your test, chi-squared is 11.2. And the p-value is 0.0107. Since the p-value is less than alpha, we reject H sub O. There is convincing evidence that the birthdays of all NHL players are not evenly distributed across the 4 quarters of the year. Okay? So that's running the test. If the results are significant, do a follow-up analysis. Meaning, if you reject H sub O, do a follow-up. Okay? So we're going to use our calculator to help with this. We're going to go hit the var button, Arrow down until you find stat.comp_list and hit enter. It should give you a list that looks like this: 7.2, 0, 0.8, 3.2. These are the observed minus expected squared divided by expected. These are the chi-square contributions. Each contribution from each quarter that makes up the total chi-squared test statistic. Okay, you want to take the top one or two contributions, so the 7.2 and the 3.2. That would be for the first quarter and for the last quarter. Okay, and you want to look at your observed minus expected. Your observed minus expected for 7.2 was 32 minus 20, which was 12. And for the 3.2 is 12 minus 20, which is -8. Here's what that means. There were 12 more players than expected born in the first quarter and 8 fewer in the last quarter. This, in fact, supports Gladwell's claim.